Hey, I hope everything is going well with yourself and your families during the COVID craziness. So today we're going to be continuing our work with gases and the atmosphere. We're first going to look at the Kelvin scale and how to convert between degrees Celsius and Kelvin and vice versa. And then we're going to get back to math a little bit and look at Charles' law and look at how the temperature and volume of the gas relate to each other. So the first thing we need to look at is the Kelvin scale. So far we've really only been talking about degrees Celsius, but now we're going to be looking at the Kelvin scale. So to sum what this paragraph up is saying, it's pretty much saying that there was this guy called Lord Kelvin who wanted to investigate at which temperature particles stop vibrating completely. Because you remember from the kinetic molecular theory that the particles within a solid vibrate slower than the particles in a liquid, and that the particles in a gas move the fastest. However, Kelvin wanted to see at what temperature the particles within a solid stop vibrating totally. Okay? So he ended up determining that at minus 273 degrees Celsius, the particles stopped vibrating, and this value, okay, is known as absolute zero. And when we say absolute zero, we're talking about 0 Kelvin. So we can say 0 Kelvin equals minus 273 degrees Celsius. Okay, so this is our absolute zero. Okay, so what we need to be able to do is we need to be able to convert between Celsius and degrees Celsius and Kelvin. So pretty much all we're going to do is to determine the temperature in Kelvin. We take the Celsius temperature and add 273 to it. And then we do the opposite to go from Kelvin to Celsius. So if we look at the first example on page 30, it says convert 25 degrees Celsius to Kelvin. So we're going from Celsius to Kelvin. So what we're going to need to do in this case is add 273. So how we're going to do that is we're going to say Kelvin equals our degrees in Celsius, which is 25, plus 273. And that's going to give us a final answer of 25 plus 273 of 298 Kelvin. Okay, so just to be clear, to go from Celsius to Kelvin, all you have to do is add 273. Now let's look at the reverse process. So it says convert 375 Kelvin to degrees Celsius. Okay, so this time we're going from Kelvin to degrees Celsius. Okay, so what we're going to do in this case is subtract 273. So what we're going to do is say degrees Celsius equals K minus 273. So that's just going to be 375 minus 273, and that'll give us a final answer of 102 degrees Celsius. Don't forget your units, that's super important. Okay, so now we're going to look quickly at Charles's law. So we've looked at Boyle's law already, and remember Boyle's law was that temperature and volume of the gas are inversely proportional. But to sum up the writing here in this blurb, this guy called Charles, he investigated the relationship between volume and temperature, and what he observed was that as the temperature increases, so does the volume of the gas. So as temperature increases, so does the volume of the gas. So as temperature goes up, he noticed that the volume also went up. This property can be explained by the kinetic molecular theory, and we're going to explain it by having a look at a system here. So what we have here is a canister of gas that is currently occupying a volume of 400 milliliters, and it's at a temperature of 198 Kelvin. And what we're doing, going from here to here, is simply increasing the temperature of the gas. So, in other words, we're increasing the temperature of the gas, and we're noticing that when we did that, the volume increased from 400 milliliters to 552. So as it turns out, if we divide the volume by the temperature for both of these, we're going to get the same thing. We're going to get a constant. So let's just dive into that a little bit more. So for this system, the volume is 400 milliliters, and the temperature is 198 Kelvin. Okay, when we put 400 divided by 198, it gives us a value of 2.02. And let's do the same for the second system. We're going to take our volume and divide it by 273. So 552 divided by 273. Also going to give us 2.02. So the purpose of this was for you to see that if we take a system, so in other words, if we take a certain volume of gas and we increase its temperature, as long as we divide the initial volume by the initial temperature and the final volume and the final temperature, it's both going to give us the same thing. So in other words, it's saying that for a gas, volume divided by temperature is always going to be a constant value. Okay. So Charles's law, in more particular, if you look at a graph of volume versus temperature, you can see that it's a straight line. Okay. So the volume of a given amount of gas is directly proportional to its Kelvin temperature at a constant pressure. So we can only say Charles' law is accurate if we're keeping pressure constant. That's important to remember. So as temperature increases, volume increases, and vice versa. So again, just to make that clear, as temperature goes up, volume goes up. As temperature goes down, volume goes down. So they pretty much follow each other. They do the same thing. Okay? Unlike for Boyle's law, where one went up, the other went down. Because for Boyle's law, it was indirectly proportional, or I should say inversely proportional. Whereas for Charles' law, it's directly proportional. And this is the major equation that you need to remember. V1 over T1 equals V2 over T2. And the way I was taught in high school how to remember that is that Charles watches TV upside down. And that's helpful because the V is over the T. So Charles watches TV upside down. That way you can remember that it's V over T instead of T over V. But let's look at a sample problem really quickly. So it says a gas sample at 40 degrees Celsius occupies a volume of 2.32 liters. Assuming the pressure is constant, if the temperature is raised to 75 degrees Celsius, what will the volume be? So remember from our definition of Charles' law, we are only talking about temperature in Kelvin. So we absolutely always have to make sure our temperature for these Charles' laws problems is in Kelvin. So in order to convert our temperature in Celsius to Kelvin, we're going to add 273. So we're going to put in our calculator 40 plus 273. That's going to give us 313 Kelvin. And our second temperature is 75 degrees Celsius, so again we're just going to add 273 to that. Okay, we're going to get 348. Okay, so now what we're going to do is set up our equation. So remember, Charles' law is V1 over T1 equals V2 over T2. And again, it's always a good idea to write down what all of your knowns are. Okay, so let's set that up. So we're going to say 2.32 liters divided by 313 Kelvin equals what we're trying to find. So we'll just leave that as V2 divided by our final temperature, which is 348. Okay, so in order to get V2 by itself, we just multiply both sides by 348 so that it cancels over there. So we multiply both sides by 34 Kelvin. Okay, and then the Kelvin on here cancels with the Kelvin on top, so we're only left with liters. So you type that into our calculator as 348 multiplied by 2.32, and then we would divide that by 313. Okay, and it turns out V2 is 2.58 liters. Again, don't forget your units. So we have to do a common sense check. Does this answer make sense? So the initial temperature was 40 degrees and the final temperature was 75 degrees. Temperature has increased, so we would expect volume to increase as well. So temperature went up. We would expect volume to have gone up as well. And our volume did. It increased from 2.32 liters to 2.58 liters. Okay, let's do another example. So we look at page 33, question 1. It says the temperature inside my refrigerator is 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and a volume of 0.50 liters, what will be the volume of the balloon when it is fully cooled by the refrigerator? So again, the first thing I'd like to do was write all the stuff I know. So T1, V1, T2, V2. So the initial temperature in this case is 22 Celsius. Okay, and it says the refrigerator is 4 degrees Celsius, so that's going to be the final temperature. The initial volume is 0.5 liters, and we're trying to find the final volume, V2. So we'll just put a question mark. So again, all of our temperatures have to be in Kelvin first. Don't ever forget that. So we're just going to add 273 to each of those values. So 22 plus 273 gives us 295 Kelvin. And then we're going to do the same for 4 degrees. So 4 degrees plus 273 equals 277 Kelvin. So let's remind ourselves of what the formula is. It's V1 over T1 equals V2 over T2. Okay, so our initial volume is 0.5 liters divided by our initial temperature of 295 Kelvin equals our final volume, which we're still trying to find, divided by T2, which we know is 277 Kelvin. So again, we want to get V2 by itself, so we multiply both sides by 277 Kelvin. That cancels, 277 Kelvin. The Kelvin cancels, so we just put into our calculator 277 times 0.5 divided by 295, and that's going to give us a V2 of 0.47 liters. So again, let's do a common sense check. Temperature went from 22 degrees to 4 degrees. You know, we put something in the freezer, so obviously the temperature has gone down. And because temperature and volume are directly proportional, we would expect volume to go down as well. And it did. It went from 0.5 liters to 0.47, so it makes sense. Okay, so I think we're pretty much good there. So the only thing that you might have issues with once you memorize the equation and how to sort of do it is the algebra. So I just suggest having a quick look through the notes, trying them out, and see if you get the right answer. And if you don't, just ask me or Mr. C for help. And that's pretty much it. We're going to end the video here. Have a good one.